Alright guys, so in this problem we're going to consider what are called interacting systems. So in this example we have two blocks in contact with each other, M1 and M2, and we're going to apply force F to the block on the back, and we're going to have these blocks moving on a surface without friction, just to make things simpler. And the first question that we want to consider here is, what is the acceleration of the system? So in this problem we're going to have M1 and M2 moving together, and they would accelerate due to the force F, and we would like to find out how much is the acceleration. Now M1 and M2, it seems kind of obvious, but it's worth mentioning here that M1 and M2 are going to be moving together. Everybody knows that if you have two objects in contact with each other and you push on the back object, then both move forward with the same kind of motion, the same acceleration. So this is because if, for example, M2 were to move not as fast, did not have the same acceleration as M1, let's say less acceleration, then M2 would be moving through M1. So assuming that these two objects are reasonably strong and rigid, that is not the case, that cannot happen. Therefore M2 must be moving in front of M1 at the same rate as M1. It wouldn't make sense also for M2 to accelerate faster, because then as M2 loses contact with M1, there wouldn't be any reason why M2 would accelerate. Clearly M2 is accelerated due to the push that it receives from M1. So clearly the acceleration of both blocks is the same, and we'd like to find how much is that acceleration. So for this particular question, it makes sense and it makes things easier to consider the object of interest to be both M1 and M2 together. So the object of interest in our free body diagram is going to be this dot that has the mass M1 plus M2, and we're going to be putting in your free body diagram the forces that are coming from the interactions of our object of interest with all of the objects that are outside of that oval, red oval that I drew there. So what is coming from outside of the system is going to be able to apply forces to the system. So the first force that we can consider is the interaction between the object of interest and the table. That's called the normal force, and this is going to be in the upward direction. The object of interest also interacts with the Earth. That interaction is called the gravitational force between the object of interest and planet Earth, and that force can be written as M1 plus M2 multiplied by G, the weight of the object of interest. The other force that results from the contact between an agent and the object of interest is the capital F force that we have in our picture as red. That force is coming from maybe a hand or some other agent pushing on the object of interest. Whatever that is, we just know that there is a force and we're calling it F. Since there is no friction, that's all the forces that we have acting on the object of interest. And with our completed free body diagram, then we can proceed to write Newton's second law, which tells us that the force in the x direction, the net force in the x direction, there's only one force, so the F is the same as the net force, is equal to the mass of the system times the acceleration. The mass of the system is M1 plus M2, so F equals M1 plus M2 times A. So from that, we can solve for the question, which is, what is the acceleration of the system? So we reach the conclusion that the acceleration is the applied force divided by the sum of the masses. Alright, so for this question, it seems a good idea to consider the object of interest, both M1 and M2 together, as if they were a single object. And what if the force was now, to calculate the question might be to calculate the contact force that object 1 applies to object 2. I'm going to call this force F1 on 2. So what is that force? So consider M2. M2 is going to be accelerating to the right. We know this is going to happen, and clearly the only agent that could be producing or applying that force to M2 is M1, because M1 is the only thing that is touching M2 that can apply a force horizontally to M2. The other object that is touching M2 is the table, but the table cannot push M2 horizontally. So this force that we call in the contact force that 1 applies to 2 is going to be going to the right. Now, how much is this force? To write or to find how much is this force, we need to write or consider the object of interest to be m2, and we're going to apply Newton's second law for m2. So free body diagram for m2 shows us that there is a normal force with the table, that m2 has a weight, and horizontally the only force acting on m2 is the contact between 1 and 2, so that's F12 pointing to the right. There's no friction, there is nothing else touching m2, so we're done with the free body diagram. Those are the only 3 forces acting on m2. And in the horizontal, or in the x direction, Newton's second law tells us that, wait, let's not get there yet. One question to consider here is, why do I not include the force, for example, the push, the force in red? Why is that not included in our free body diagram? Another question is, why are we not including in the free body diagram the force that 2 puts on 1? So the answer is that free body diagrams involve only the forces acting on the object of interest. So why is capital F not in our free body diagram? Because capital F is not applied to M2. Capital F is applied to M1. And we're doing the free body diagram for M2, not the free body diagram for M1. So the forces acting on M2 are only the normal Fn2, M2g, and the force that 1 puts on 2. Now, why not include the force that 2 puts on 1? Clearly, block number 2 is putting a force on M1, and that's force we're going to discuss again in the next question, that it goes to the left. But shouldn't that force also be included in the free body diagram for M2? So here we go back to what we said about the free body diagram. It shows the forces acting on the object of interest. We're not going to be adding to the free body diagram the forces that the object of interest puts on other objects. This is not to be included in the free body diagram. One more time, the free body diagram contains the forces that are acting on the object of interest. Coming from other objects, it reflects what other objects are doing to the object of interest. What the object of interest is doing to something else, we're not concerned about that at the moment. We're focusing on what is happening to M2. Okay? And what is happening to M2 is that the table is pushing it up, the block number 1 is pushing it to the right, and planet Earth is pulling it down. That's what's happening to block number 2. So get rid of those forces. We only have 3 forces acting on M2. And horizontally, one more time, we only have 1 force, and that is the force that 1 puts on 2. And according to Newton's second law in the x direction, that force should be the mass times the acceleration of the object. We're considering the motion of M2, so the mass is M2, and the acceleration A is the same as the acceleration that we calculated previously. It must be the same. M2 has the same acceleration of M1, and both together have an acceleration that we already found previously. So what we can do now is replace. In part A, we got that the acceleration is F divided by M1 plus M2. So we can replace that. And that is our final answer for the force that block 1 is putting on block 2. This is the force that makes sure that M2 accelerates at the same rate as M1. Otherwise, as we said, the objects would break through each other's surfaces. So let's consider now what's the force that block 2 puts on block 1. So the force that we're talking about is the force that to the left acting or coming from M2 acting on M1. How do we know that this force is to the left? Well, we'll think about it. This force is the force that block 2 puts on M1. Could block 2 pull on M1 to the right? With M2, should it be pulling on M1 to the right, making it go even faster than it would go if M2 wasn't there? So clearly that doesn't make sense. So the only possibility for the force that 2 puts on 1 must be to the left. The presence of m2 in front of m1 should slow down the motion of m1. You clearly can run faster by yourself than having somebody in front of you pushing you backwards. So this is what m2 is doing to m1. It's pushing it backwards. So this force is what we call in F2 on 1. So how do we find how much is this force? So again, now we're gonna, what we did before was to focus on M2, now we're gonna focus on M1 and write Newton's second law for M1. So M1 is this dot, and we're gonna attach to it all the forces acting on it. So M1 is in contact with the table, so that force is upwards. M1 is attracted by planet Earth, so that force is downwards. M1 has this agent, whatever is applying that red F, capital F force, that force is applied directly to M1. So we have to show F in the free body diagram for M1. And then we have the force that 2 puts on 1. We already decided that it had to be to the left, and there's no friction, so we are done. M1 has a free body diagram with 4 forces. Clearly in the vertical direction, those 2 forces, Fn1 and m1g, must cancel, but horizontally, those forces, F and F2 on 1, they do not cancel, because we know that there is an acceleration. m1 is accelerating as much as m2 is. So the sum of the forces in the x direction is not 0, it's equal to the mass of the object of interest, m1, multiplied by a. We are after solving for F2 on 1. So we can replace the value of a that we know, that we calculated in part A. We're going to move F2 to the left. Not to the left, it's already on the left. We're going to move it to the right with a positive sign. And we're going to move, yeah, that's what we're going to do. Just a second, right there. So we're going to move F2 on 1 to the right-hand side of the equality. And we're going to move the term m1 times f divided by m1 plus m2 to the other side. So that goes with a minus sign. And we have then that F2 on 1 is f minus m1 times f divided by m1 plus m2. There is a few more things that we can do to make this expression look a little nicer. We can, for example, factor out the f, since both terms have an f. We can factor it out, so f2 on 1 is equal to f factor of 1 minus m1 divided by m1 plus m2. One more thing that we can do, algebra-wise, is to take a common denominator, m1 plus m2. Now the numerator would be then m1 plus m2 minus m1. We can now cancel m1, and what do we get? The force that 2 puts on 1 is m2 times f divided by m1 plus m2. Does this look familiar? Well, this is exactly what we got when we found the force that 1 puts on 2. Same result, m2f divided by m1 plus m2. So we have found here, using only Newton's second law and using different objects of interest, knowing that the objects move together, we have found the following result, interesting result, that the force that 1 puts on 2 is equal to the force that 2 puts on 1. So object 1 and object 2 are interacting with each other, they are in contact with each other, they are pushing on each other, but those forces, we found them to be equal in magnitude. The directions, as you can see, are opposite. By the way, the magnitude of those forces is m2f divided by m1 plus m2. But what we can say then is that in vector notation, considering those vectors, f1 on 2 and f2 on 1, those vectors are equal but opposite. So f1 on 2 is equal to minus f2 on 1. This doesn't tell us which force is positive or negative, it just says that the forces are pointing in opposite directions. So this is actually a special case, or a special case of Newton's third law, especially in the sense that we have derived this in a specific context of M1 and M2 and the force acting on them. But as we're going to discuss in the next video, Newton's third law is a very general statement. It's a law of nature that is obeyed in all situations, in all cases. So we have proven here that F1 on 2 equals F2 on 1. But like I said, there is no need to prove that. This is a law of nature that says that every time an object interacts with another object, A interacting with B, well, A will put a force on B, and B is going to put a force on A, and those two forces would always be equal in magnitude but opposite in direction. Alright, I'm gonna leave it there. I'll see you in the next video.